strength, if it exists, right? In theories with no field strength, there's no field strength in the anomaly polynomial. And of the curvature, each of which is thought of as a two-form. In situations in which, when we're thinking of the curvature, we're thinking of it as a two-form with the two-form indices mu nu, and then AB as being Wehrbein indices. Okay, so SO10, it's an SO10 gauge theory from the point of view of kinematics. Okay, and right at the end of the last class, we began to look at type 2B theory. Okay, so first, let's look at type 2B theory. In this theory, let's remember that the massless fields were a graviton and the dilaton, B mu nu and a Ramond-Ramond two-form, and then a self-dual four-form field or a self-dual five-form field strength. Okay, in this theory, there's no gauge field. Okay, so there's no analog of F. The anomalies are all in the gravity set. Okay, so what were the anomalies? There was an anomaly associated with the Rarita-Schwinger. Okay, there was an anomaly associated with the ordinary gaugino. Okay, there's a minus between these two because this is chiral, this is anti-chiral. And let me see, let me work with Polchinski. I think Polchinski and Green-Schwarz-Witten have slightly different notation here for their eyes. Yeah, what Polchinski puts a 2 here because for him each, for Witten one complex spinner is I, for Green-Schwarz-Witten. For Polchinski one real spinner is I. You know, so there's a small, I'm through the course where possible I will stick to Polchinski's notations. So okay, and then there's of course plus the self-dual. Self-dual is the four-form potential or the five-form field strength. Okay, now if you want detailed formulas for these quantities in every dimension, they're listed in terms of generating functions in Green-Schwarz-Witten. Very beautifully listed. Okay, this is something that I could list for you on the board, but since we're not planning to derive these things, I won't do that. You can go and look in Green-Schwarz-Witten for the general formulas, or in Polchinski for the formula for d equals 10. Okay, the important thing is that each of these guys are very complicated. We wrote down one of them yesterday, last class, right? Let me just, for instance, just to give you a sense of how complicated these things are, just sticking to the gravitational sector because that's all that there is. For every what we call, okay. Now this I think Polchinski calls 56 and 8. Green-Schwarz-Witten calls them 3/2. Okay, Rarita-Schwinger and ordinary spinner. If you look at I8, the anomaly due to one of these gauginos, okay, it is trace r to the 6 by 725760. Minus 225 trace r to the 4r square divided by 552960. Minus 63 trace. Divided by 1327104. Okay, you see, you can see that though we're talking only about numbers here, the numbers are pretty weird. Okay, you get other sort of weird numbers for 56 and for self-dual, But the numbers are such that when you take twice of this minus twice of that minus plus this, it just sums to 0. Why are there no f's? Because type 2b theory doesn't have a gate symmetry. Okay? So this the formula for I can be written down in terms of R plus f in terms of traces of f in the representation in which it appears. Now in a theory where there is no f, it's like having f in the trivial representations, all those traces are 1. Okay, so there's a general formula in terms of R and f. In this case, you just set all the trace f's where, right? Well, they're not them, right? Okay. Fine. Clear that there's no f here just because there's no field strength in there's no gauge field in type 2. I mean, it's that simple. Okay. Now life gets more interesting in the type 1 theory. Type 1 heterotic is the same thing. Because you remember we discussed that, well, at least type 1 and SO32 heterotic is the same thing. Because as you remember we discussed that at the level of supergravity those two actions are the same by a field redefinition. Okay? So let's see what's going on here. First we'll do the algebra, then we'll try to understand the physics. Okay, so now we try for type 1, so we get I1 is equal to, well, you see, what we have in this case is we still have a 56, but only one of them, R comma F. Now there's a field strength, right? Okay, however, this guy, the 56, is uncharged under the gauge group. So that is effectively, right, type 1 has gauge fields. These come from the open string sectors. Okay, only matter, integrating on matter fields in loops contributes to the anomaly for F, only if those matter fields are charged under that field strength. So this is basically only one thing that will contribute to the F anomaly. Okay, that will be the superpartner of the gauge field. Okay. Now how does this go? Yeah. So there's minus I8 of R. This is the spinor in the gravity multiplet, which once again is uncharged under the field strength. Okay, it's the spinor that descended from the type 2b. Okay, but now in addition we have chiral spinors, okay, that are the superpartners of the gauge field. They're the n equals 1 matter multiplet. Okay, so we have plus I8 of RF because these guys are charged under the F. Okay, and they're charged in the adjoint. So when we take traces, that will be traces in adjoint. Okay, so this will be the anomaly polynomial. This is the anomaly polynomial for type 1. Okay. Okay. Now, if you just do some algebra, you find that this guy is just not 0. Okay? Certainly, if you do some algebra for some arbitrary gauge group, you find it's very far off from 0. But if you take, even if you take the case SO32, you still find that it's not 0. Okay. So now however, the whole thing actually is anomaly free, and we have to understand how. Okay? For a long time, till 1983, 1984, people thought type 1 theory was nonsense because it was anomalous, because this thing didn't cancel. First I'm going to tell you about the trivial algebraic part, and then the second more interesting physics part. Okay, so let's first look at the more trivial algebraic part. For that I'm going to actually write down a formula. Okay, I'm going to write down what I8 Okay. So first let me focus on the parts that involve the gauge field F, because that doesn't mix with this and this. It's just all from here. Nothing else involves F. Okay. So let me write down I8, and this is what we find. We find minus trace f to the 6 by 1440 plus trace f to the 4 trace r squared, sorry, plus trace f to the 4 trace r squared by 2304 minus trace f squared trace r to the 4 divided by 23040. Yeah. Minus trace f squared trace r squared divided by 1327014. No, 27010. Okay. This was I8. We come back to this in a moment. Okay, and then there is I56 of R. I'm just going to write them all. Despite saying I wasn't going to, just because the algebraic point will become clearer. Not okay. I'm going to write them all down. Just okay. So you get some appreciation for what's going on. Sorry, 495 trace r to the 6 divided by 725760. Okay. Minus. Okay. Now 225 I'm so sorry. I even forgot the pure anomaly parts. Sorry. Plus n, and I'll tell you what that n is. It's trace r to the 6 by 7.
This is an I8.
In I8. Sorry. 5760 minus trace r squared trace r to the 4 minus 225 divided by 552960 plus 128 trace r squared divided by 1327010. Now what was this n? You see, we're dealing with the adjoint representation here. So anything that is independent of f has trace of identity. Okay? So that's promoted n, namely the number of elements in the adjoint representation of the gauge group. Okay? So if we were doing SO32, that would be 32 into 31 by 2, so 16 into 31, so some huge number. Okay? This is I8 here. This is the contribution to the anomaly from the gaugino, the superpartner of the gauge field. And then we have to add the contribution from this guy and from this. Okay. Let me write it down. Fine. I keep dithering between writing and not, but let me do it. Let me just finish it. So we've written the worst one. I56, so these are easier because they're purely gravity, right? So I56 is minus 495 by 725,760. Trace R6 minus 225 trace r to the 4 trace r squared by 52960 minus 63 trace r squared cube over 1327104. And then of course there's I self-dual, but we don't need that for this case. The I8 is simply the same as this I8, restricted just to gravity and setting n equals 1. Okay? And now another way of saying this factor of n is that as far as gravity is concerned, each component of that matter field is identical, and there are n of those. Right? Because of the multiplicity. Okay? So that's I56, that's I1, and you know what this I8 also is, right? It's just this part of it with n equals 1. Okay? So then we can write down the whole thing, I56 minus I8 plus I. This is something. Now it is a matter of algebra to reprocess this formula into a form that looks a bit nicer. I'm going to tell you that nicer form. It turns out that whole thing you can check just pure algebra, nothing else. 1440 into minus trace f square f to the 6 plus 148 trace f squared trace f to the 4 minus trace f squared cube, okay, plus n minus 496 times trace r to the 6 by 725760 minus y4 x8 y4 is equal to trace r squared minus trace f squared, and x8 is equal to trace r to the 4 plus trace r squared by 4 minus trace f squared trace r squared by 30 plus trace f to the 4 by 3 minus trace f squared squared by 900. Okay, so claim that uncivilized looking expression on the right hand side can be rewritten to look like the uncivilized looking expression on the left hand side. And you might be wondering, what the hell? I mean, why should I care?
Looks like there are 3 terms multiplying at n minus 46.
What? In the book? Really?
Trace r power 6, trace r power 4 r squared, trace r square whole cube.
Oh, so this is a new version. Sorry. Yes. I'm sorry.
These 3.
This is the new version of the book. I should correct that. Sorry. Thank you.
I think That says I8 is different in the old one.
It is different.
Yeah, so this denominator has 1 at 432, which is
Could
the
I?
fourth. Yeah.
Thank you everyone. This one? 1, 2, 3, 4. Trace f squared, trace r squared squared, 18432. Okay.
And the last bracket, those coefficients like 122 and 128 are not there.
This
Yeah.
these 225
Sorry,
Yeah.
225.
and 120. Thank you everyone. Thank you everyone.
And it's a plus for all.
Yeah. Okay, thank you. Thank you. Yeah, of course, all these would be fatal errors if you try to go from here to there. Thank you. Okay, nonetheless, you can. Now, we've written this expression in terms of 3 terms. There's this guy, and this guy. We have to deal with all of them separately. Now, I've written it this way, people have written it this way, for the following reason. In the case of SO32, let's compute n. Okay, so n is equal to 32 times 31 by 60. By 2, sorry, which is equal to 16 times 31. Now, 30 16s are 480. So 31 16s are 496. Okay, so this uncivilized looking piece in our special case is not there. You're probably less familiar with the adjoint representation of E8, but it's a fact that the adjoint representation of E8, the number of elements is 496 divided by 2. So that E8 times E8 has 496 elements. So also for E8, this guy is 0. So second line looked bad but is actually not there. You see, it was very important that we got precisely the gauge groups we got. Had we got SO34, it wouldn't have worked. Now SO32, do you remember how we got where we got SO32 from?
From the self-dual in heterotic.
I was thinking of type 1. Okay, but both of them, yeah, each of them has their own way of thinking. But let me ask you first for type 1. For type 1, where did we get SO32 from?
From this open string amplitude, the cross cap.
From the tadpole cancellation.
Yeah.
Okay? You see, had the with the number of branes being anything different from 32, we had a tadpole for the dilaton. Okay? So this expansion point was somehow an inconsistent expansion point. Actually, space would curve and various other things. In fact, we would actually also get tadpole for gauge fields. So it would have been an inconsistency. There would have been a serious problem here. Okay, we didn't work it out that way, but if we get a tadpole for the dilaton, there's actually also a tadpole for other things. Okay, so string theory, without precisely 32 branes, had a deep problem, at least if we try to expand it around flat space. And that deep problem shows up now just from a low energy point of view. Okay? If we just forgot about that problem, said forget about it, let me write down a low energy theory pretending I could work with any number of branes in the vacuum, we would get the supergravity theory with arbitrary n, with SO, n being the adjoint of an arbitrary SO, SO something, and we would find that that term just does not cancel, and theory would just have been anomalous. Okay? So the 32, which came from one consistency requirement from string theory, you can also see purely from a low energy point of view, which is extremely satisfying. Okay?
But, even with that term gone, the whole thing doesn't.
Coming. Now let's look at the first line. The first line looks non-zero, except there are these things called character polynomials. Are you guys familiar with this? That, if in group theory, you write down some object in terms of, let's say, some representation, you can rewrite. So you're dealing with an algebra element, an element of the algebra of the group. Now, the element of the algebra of the group, you can look at it in any representation. Okay? You can look at it in the fundamental representation, the adjoint representation, any representation you want. For people who study group theory, the following thing is a very useful thing. Given an expression, let's say some polynomial, of an algebra element, a trace of products of traces of an algebra element, like trace f squared or trace f to the 6, okay, in a particular representation of the group, how can I reproduce that same number from polynomials in the fundamental representation? Do you understand what I'm saying? You see, there's the same information in which element of the algebra you are in any representation. Because the only information is in the TAs. Suppose you write an algebra element as CATA. The information about which algebra element you're looking at lies in the CAs. Okay? But let's say this algebra element was F. Then you take trace f to the 6, for instance, in one representation. You get a different answer from trace f to the 6 in some other representation. Now, in group theory, this is a very useful question to ask. Can you write all these polynomials in terms of the polynomials in the fundamental representation? So, the same function of C's, but written in terms of traces of polynomials in the fundamental representation. Group theorists love doing these things. These things are called character polynomials. Okay? It's done all the time. Done both for algebra elements as well as for group elements. Okay? So now, the thing here is that there could be hidden relations between trace f to the 6 and trace f to the 4 and trace f squared, because we're dealing with these f's to the 6, f to the 4 and f squared in this funny adjoint representation. These traces in the fundamental representations are just traces of n cross n matrices. Okay? And there are no relations between them until the number of trace elements becomes larger than, say, let's say 32. So once you re-express them in terms of the fundamental matrices at the level of f to the 6 and so on, you're not going to have relations. But in the adjoint you might. Okay? So it's a wise thing to do to just rewrite this in terms of traces in the fundamental representation. Do you understand? The expression here has all these traces in f's in the adjoint representation. That comes from physics. Where did it come from? It came from the fact that the Gaugino is transformed at the adjoint representation. But then it's just as a matter of algebra, you can rewrite traces of f squared or traces of f to the 4 in the adjoint representation in terms of traces of the same objects in the fundamental representation. Just as a matter of algebra. Is this clear? Okay? And this is what one finds. Trace in the adjoint of t squared, some f squared, for instance. Okay, I'll write it as f squared. Any object in the adjoint representation is equal to n minus 2. Now this n is different from
now this n is the
SON.
rank of the
Yes. So let's call this n and let's call this n tilde. So this is okay. N minus 2 trace t squared in the fundamental, which Pulchinski calls the vector representation.
this again f square, right?
F squared, thank you. Okay. Now, what about trace f to the 4 in the adjoint? This is equal to n minus 8, n tilde minus 8, trace in the vector f to the 4 plus 3 trace vector squared. Notice that the net homogeneity cannot change in these relations because these things are polynomials of CAs and the degree as polynomials of CA cannot change. It's just these coefficients that are rearranged to be rearranged. And similarly, there's some relationship for trace f to the 6. Trace f to the 6 in the adjoint representation, okay, is n tilde minus 32 trace f vector to the trace vector f to the 6 plus 15 trace vector f squared trace vector f to the 4.
There's no trace f squared cube term.
There's no trace f squared cube term unless the new book has. Okay, excellent. Now there's one very important point here. The very important point here is that the trace vector f to the 6 vanishes because n tilde is 32. Why is that important? Because that came from only one place. F to the 6 vector can only come from f to the 6 adjoint. Could not possibly cancel against anything else. Exactly in 32, that term goes away. Now these other terms come from 3 different places, well, from different places. So they could cancel. And if you look at it carefully, I won't swear to doing the algebra myself. Okay? But if you look at it, let's try. Let's be brave. Fortune favors the bold. Okay. So let's take this guy, f squared f to the 4. Okay, that can come only from here and here.
Yeah.
Because this is clearly f squared again.
Yeah.
Okay, so this is 1 by 48.
And minus 1.
And
So there's minus 15 from here.
yeah, and have I written it right? Just let me check. Y4 times x8 we'll come to in a moment. We want to keep y4 times x8 separate. Let's see. Let's see. Have I got it? Wait, do you mind checking my numbers in your book?
What is the page number of this?
What? This is in my book. It's page 101.
The third one is
What?
the third one, trace f square whole cube.
Oh, is it divided by 14400?
Yeah.
I just forgot to write 400. And now, but let me get this 1 by 48 business right. Just one second. Just 1 second.
Yeah, it's the same.
It's the same. Okay, excellent. Just 1 second. 6 had a 15 and this guy had a, okay, good. So now let's look at this guy. Trace f square came with the number There was 1 by 48, but that f squared went to
Integer minus
30 times f squared. And f to the 4, where is that? That's into 24. Okay, now that should cancel. That should cancel. What was the number? The last term there.
The first 15.
Yeah, right. Minus 15, exactly. 15. So this should equal 15.
Yeah,
Now,
it does.
and it does, exactly, because it's 30 by 2, so 15. Okay, so that's how this cancellation happens. Okay, and you'll have to work harder for checking the cancellation for trace f squared cube. That also works. Wonderful. So with this particular SO32, this thing is killed. Actually, you have to look at the trace identities also for E8 cross E8. Okay? There are different trace identities. But the same cancellation also works. Okay? First line and second line are just by themselves 0. But that leaves this y to the 4 times x to the 8. And you might be thinking, well, okay, y to the 4 times x to the 8 are very complicated. So we've not made much progress. But actually we have. Okay? For the following reason. Look, this whole anomaly polynomial method was designed, the whole anomaly polynomial method was designed to look for terms whose variation under gauge transformations is local, even though the expressions, even though they cannot be written as they cannot themselves be written as variations of local terms. Right? So the variation is local, but it's not the variation of something local. Right? Because had it been the variation of something local, it just was not an anomaly in the first place. That was the point. Okay? But that whole anomaly polynomial method worked by, worked with normal gauge transformations. Assuming that the gauge transformations of everything in the game is normal. And of course, the gauge transformation of field strengths, for instance, is normal. But you remember that there is one field in type 1 theory that has a weird gauge transformation. And that's the B field. Oh, the B field in the heterotic theory and the B tilde field in type 1 theory, the two form that came from the Ramon field. I'll continue to call it B. Okay? And what do I mean that it had a weird gauge transformation? Let's remember that in type 1 theory, we wrote everything in terms of our whole action was written in terms of H tilde which was dB. In type 1, this would be C2. In the heterotic, it's B. I'm just calling it B for simplicity. Minus omega 3. You remember? Omega 3 was the Chern-Simons form for the ordinary gauge field. Okay? And the point of this was as follows, that under a gauge field transformation, gauge transformation, delta omega 3 was equal to trace lambda times f. Okay? And so that this whole thing here is gauge invariant, provided that under B goes to under a gauge transformation, B goes to B plus trace lambda A. So that dB will be go to dB plus trace lambda f. What? D lambda is a constant. Oh, wait. You're right. Wait. So how does this actually? Just a minute. No, lambda is not a constant. You're right. Sorry, what did we want? Sorry, let me remember. How did the gauge transformation go? We got this straight last time. Yeah, trace lambda f. Okay. Yeah, what happened to the d lambda? Just a minute. You're right. This made no sense, right? Because this is a one form, this is a two form. Okay. And what is this omega 3? This was b of trace lambda f. Thank you, because it had to be a total derivative. Now it's clear. Sorry. Right? Sorry, this is very important. I was messing up badly. Okay, b goes to b plus lambda trace lambda f. That was the gauge transformation. So now we can ask, are there terms whose gauge variation, are there gauge variations, terms that appear on the right hand side of del dot j, that cannot appear as the variation of a polynomial, a local term built only out of the field strengths and r mu nu, but can appear as the variation of a local term built out of b, the field strengths and r mu nu. Right. So, in the traditional analysis, field theory analysis of anomalies, the question we ask is the following. I mean, the thing we say, an anomaly is an anomaly if variation under the gauge transformation of the action is local, but that object itself is not the variation of a local quantity. Now, what do we mean by local quantity? Well, some local quantity built out of, if we're looking at gravitation and gauge field anomaly, some local quantity built out of the gravitation and the gauge field. Okay? The whole anomaly polynomial method is designed to answer that question.
Yeah.
But now you see, in this game, we have another object, which is B, whose variation, which is not the gauge field or the graviton, but varies under the gauge transformations of at least the gauge field. Okay? So now let's try to see if there exists a local term built out of B and everything else, whose variation is of the form that can cancel some of the terms that appear here. If so, that's not really an anomaly, or maybe it's not really an anomaly. We'll come back to that question. Do you understand the issue? Do you understand the way out? The fact that in string theory, fields that are not the gauge field transform under gauge transformations is an element that field theorists had never thought about. So, this is an example of something that happens all the time in physics. People prove theorems, and the theorems are correct. They're correct as mathematics, but they're wrong as physics because they make wrong assumptions. That's the nature of mathematics in physics, right? It's a bit pointless being too rigorous in physics because most of the work is in modeling the physical situation in your axioms. And usually that's where theorems go wrong in physics. So there's basically a theorem about anomalies, but that theorem is basically irrelevant to string theory because the assumptions were not correct. Okay? So now let's see how this can help us.
Any theorem worth its salt must have a loophole.
There's this beautiful paragraph by Feynman where he takes off on rigor in physics, which I completely agree with. Oh, what an utterly pointless exercise it is. Okay. Okay. And you know, this, by the way, despite all our pretensions, this is very much the style of string theorists. You see, 3 pieces of evidence for a duality, it's true. The original evidence for most dualities was counting. And Hawking had this famous statement, right? That there are about as many people in France as in England. I don't think that's a good reason to identify them. No, but I mean, pragmatically speaking, we don't do rigor in string theory, really. Right? We may sometimes pretend to it. But we don't, and that's very healthy. You move on. Okay. So now look, we want to see what additional terms we can get, what additional local terms we can add to action to generate anomaly pieces that would otherwise be hard to get. Okay. So now let's look at this. Suppose I take B, wedge, any object, like for instance trace f to the 4, but any object. So in general, this is an example where I'm taking B wedge alpha such that D alpha is equal to 0. Okay. Now, under my, this is like a Chern-Simons term. It's kind of Chern-Simons term we haven't considered so far. Why not? Because this Chern-Simons term is 4 derivative. You remember when we were discussing supergravity, we were very careful to restrict ourselves to 2 derivative supergravity. That's what the supergravity people worked out for us. That's the extent to which these actions were unique. But suppose there was a term like this in string theory. By the way, in string theory is different from field theory.
Yeah.
Because string theory, you can't hide behind, we can change the definition of the theory at short distances. We can add a counter term. Things are either there or they're not. We have the rules to compute everything. So here we're going to devise a plausible mechanism that we're going to have to check in string theory.
So this is a uniquely stringy effect, this term.
This term is by itself not a uniquely stringy
No,
effect.
I think it's still a sort of admits a field theory description.
Yes, but in string theory, what I'm going to be saying, I'm going to give you a possible way out. And then in string theory, that way out is either true or false. Okay, it's not like in field theory where you can change the definition of the theory to make it true. String theory, we don't have that with us. First, I'm going to give you, from a low energy point of view, a way that we might be saved. Then we'll have to check that we are saved. Okay, but the first part is very important. Okay, so now let's look at this. Look now under a gauge transformation of under a gauge or a zero form gauge transformation, the normal gauge field gauge transformation. How does this transform? Well, we've just seen the variation under a gauge transformation. So delta of this is equal to trace lambda f times alpha. Okay. Now, delta of this is trace lambda f times alpha. Okay. Now, under now let's look at how the descent relations go. If we go up the descent ladder, this will be replaced by a wedge f, really an omega 3.
I'm sorry, but why don't you consider variations of alpha itself?
Where?
I mean, alpha is some trace f to the 4, right?
Alpha is whatever it is.
Yeah.
But it's something that is by itself gauge invariant.
Okay. This is a gauge variation, I see.
Yes. So we're looking at the transform. So for instance, trace f to the 4, right?
Right, yeah.
Okay. So now we take trace of lambda times f. Sorry, maybe I didn't say that clearly. Whatever this multiplies has to be gauge invariant.
Yeah.
Okay. So I take trace of lambda times f times alpha. Now we go up the descent ladder. Okay, so we go up here, we get trace omega 3, and we go one more up to the anomaly polynomial. This becomes trace f square.
Ah.
Okay, so you see that any object here which has a trace f square times anything gauge invariant, in the anomaly polynomial can in fact be written as the variation
Yes.
of a local counter term. That del dot j can actually be written as a variation of a local counter term. That local counter term would be a Chern-Simons type term involving b and that whatever that other things. Is this clear? Now look at this guy. Y4 has an f square here. So every term involving f square here is of this form.
Oh, yes.
Okay, so we have dealt with half of y4. But we're still left with the trace r squared times the other stuff. Now how can that work? Well, let's see. Suppose, remember what our h was? Our h tilde was equal to db minus db minus what was it? Omega 3, right?
Yeah, I mean, you just
Trace omega 3. Yeah. Omega 3. Now, suppose that the right expression for h tilde was this plus trace omega 3 SO10. Suppose that was the correct expression. The first question you ask me is, well, if that was the correct expression, why didn't we see it in supergravity? And the answer is simple. Trace omega 3 is one derivative when it's gauge theory, but two derivatives when it's gravity, because the spin connection is like the curvature. And the curvature is two derivatives. Whereas omega 3 there is like a by f. A is zero derivative and f is one derivative. So while gravity and gauge theory work kinematically the same way, there are many important differences. One of which is that the field strength for gravity is two derivative, whereas the field strength for gauge theory is one derivative. So now if we took h square, that object would never show up at two derivative order, because the minimum number of derivatives that you would have to have involving that object would be 3.
So, I mean, would the term, but the term would show up if we had a full
String theory
non-linear completion of type 2A supergravity. I mean,
No, there was, what we wrote down 2-3 lectures ago was a full nonlinear completion. But it was just a nonlinear completion at two derivative order. Now you see, string theory is not two derivative. It has corrections.
And all.
So one of the corrections might be encapsulated in h going to this.
So in this sense, this is a uniquely stringy effect. I mean,
Yes, yes.
Not coming from the low energy theory, but
Something that, yes, string theory would have to tell us.
tell us. I mean, yeah, I mean that we can't just insert by. I mean, string theory completely specifies.
Specifies it. At the moment, we are involved in the exercise of asking, how could it possibly work? Then we have to check that it does work that way. Is this clear? Okay. Suppose this was the case. Then the gauge transformation here would be modified to b goes to b plus lambda r plus a minus trace of lambda SO10 times r, just the same way. And then our anomaly polynomial would be f square minus r square. Anything that was f square minus r square minus f square times anything would be cancelled.
So just y4 itself would be done.
Anything, this whole, anything proportional, y4 times anything.
Yes.
would be cancelled. Right? So suppose this was the case, then this thing was not really an anomaly. Okay? Why was it not really an anomaly? Now let's say it again. This object here represents a lack of gauge invariance under one loop diagrams of the supergravity part of the Lagrangian. But there could have been a term in the Lagrangian just at tree level, just in the action itself, that by itself was not a gauge invariant. What term would that have been? Precisely this one. The term would have been integral of B wedge y4. Under a gauged, under U1 gauge, under an SO32 gauge transformation, this transforms like trace lambda f, wedge y4, and that's not zero. It's not a gauge invariant term, and that's precisely the point. Because it's not gauge invariant, but it's a local term. Okay? This local term here has a gauge transformation that is precisely of the form to cancel the otherwise uncancelable.
No, will it be gauge invariant if integrated over the?
No, not even when integrated, because it's not d of something. It's trace lambda f. Right? So it's not that kind of Chern. It's not the kind of Chern-Simons term that was gauge invariant. This was another reason we wouldn't have written it down. It was just not gauge invariant. But actually, if we'd written this down, that could allow us to live with the kind of gauge invariance we have, gauge non-invariance we have from the supergravity sector. Is this clear? B wedge x6, sorry, x6, thank you.
X8.
X6.
No, this is.
Oh, this is 8. Thank you. X8. You're right. B wedge X8, and this should be a 10 form, right? Because we're writing down. Thank you. B wedge X8. Thank you.
Yeah. So one question. So this incorporates in a way the first correction to let's say one higher order in derivative. So what is to say that we don't need to keep any further orders in derivative to keep it anomaly? I mean, if why just this one and not any?
We've already seen what anomaly we're producing. Okay? Now if this term is there, that will get rid of, you remember that loops, there's a theorem that says that they can't get anything further from one loop exact. So this is the full anomaly from there. So this had better be only this in order to keep the whole theory anomaly free. Okay? Maybe people have done a systematic analysis of asking more clearly what terms you can add of this form. That I'm not aware of. Somebody must have done it. But for this particular theory, this is all we need. Because we know the anomaly from the massless sector, and this would cancel it. So if this is there, we're good. Okay? So this is a proposal you can make. Proposal, in string theory perhaps, this is the case. Now, we have to check. How would you check? Well, the easiest way to check is ask the following question. We know that the string theory effective action has a term that's h squared. So if this term is here, what does it mean? It means that there is a term that is, for instance, dB wedge. So there are two things we can check. First, does this term appear in the action? I mean, in h square, is it completed with this extra piece? And secondly, is this Chern-Simons term there? Okay, both things we have to check. Okay, so how do we check the first term? The first question. The first question is this. See, omega 3 or this guy. Firstly, how would we check that this was there? Well, this is a wedge f, so it's 2 photons. Right?
Yeah.
So it's some 2 photon kind of object. So what we're saying is that there is a diagram that is like a scattering between B, A, and A that is completely dictated by tracer, by dB weight, this Chern-Simons term. It's a very easy thing to check. It's just a 3-point function. As you know, 3-point functions are terribly easy to check. So in our next round, which starts probably next class, when we go back to the world sheet, this is the kind of thing we'll do. We'll write down the vertex operators and check these diagrams. Check that they're actually there. Okay? Similarly, there is a B, H, H that's predicted by this term. That's either there or not. Okay? We check it. If we find that it's there, that tells us that that completion is happening. Second, what about this guy? Well, this guy, it's similar. Let's see, where is our X8? So for instance, we could look at the term trace f to the 4 in that. That is a term with 4 photons. Okay, times B. Okay, we should check that that term is there in string theory. We will check it. We will actually do it in class, or at least go through some part of checking it. And we find that actually they're there, and with exactly the coefficients needed to cancel these.
And these are all tree level.
Tree level calculations. Simple tree level, nothing deep. Okay, and from the point of view of string theory, how does the anomaly cancellation happen? Well, there is this diagram, which is some schematic for the one loop diagrams. Okay, there is this diagram, which is a schematic for the one loop diagrams that produce, let's say, the term which was f squared, I've rubbed it out, f squared in y4 and f to the 6, f to the 6 in x8, maybe an x to the f to the 8 in x8. Let's say that we were doing the pure photon thing. Okay, so the 6 photons. Such a term is there. But there is a term, as we've just seen, this is the Chern-Simons term, that takes 4 gauge fields and exchanges a beam union. And because of this term, there is this term.
Produces 2 A's.
Can produce 2 A's. Okay? The lack of gauge invariance of this vertex
Is compensated
turns into a non-gauge invariant answer for this whole thing, which exactly compensates the non-gauge invariance of that diagram. If you sum those 2 diagrams together, and you get something completely, perfectly nice and gauge invariant. Okay? Now, as you can see, this is a pretty complicated thing. And superstring theory, was invented, or basically not the heterotic string, but like say type 1 theory, was invented sometime in the 70s. And however, people had no confidence in it. Because you invent the theory, you get a low energy effective theory, you check for anomalies, and it didn't work. Okay? Type 2 theory, type 2B theory worked, but it felt odd that one theory works, the other theory doesn't. And also at that point, people were very much driven by the hope of connecting with phenomenology. Type 2B theory had no non-abelian gauge fields. Whereas type 1 theory, because of these E8, E8 appears in grand unified models. The E8 was thought of as a very promising thing for grand unification. Okay? But it didn't work, it was not anomaly free. So, what were we talking about? Whether or not it's reasonable, when this anomaly cancellation mechanism was first understood by Green and Schwartz, following up on work by Witten and Alvaro-Gomez, when that was first understood in 1984, that had a huge psychological impact on the field.
First superstring revolution.
First superstring revolution. I remember Ian Affleck telling me, we were going on a hike somewhere in Argentina actually, and he was telling me that he was a professor at Princeton at that time. And when he went for a year's sabbatical to Paris. This was like early 1984. Then he came back in early 1985. Nobody was doing anything but string theory. He felt totally out of it. There was phase transition. Because this obstacle had gone away, because of the personality of Witten was extremely excited about it. And he was extremely smart and extremely infectious. And because of other people, gross. Anyway, so the physics you can see on the board. The psychology is maybe harder for you to understand because it comes from a certain mindset and from what people thought was important then and so on. But it had a huge psychological impact. And it led to the serious study of string theory as a mainstream subject for the first time. Before that, it was sort of on the fringes. And so this anomaly cancellation mechanism played a huge role in the history of our field. Not that we usually talk about history, but just to say. Okay. Now, you may wonder about how it's possible for a one loop effect to cancel against a tree level effect. You may wonder, how could it be? Aren't these terms different orders in G string? The problem with this argument, this point, is that you have to be very careful about the natural Ramond fields. And you've encountered this before. I don't know if, without explaining too much, when we were writing down our supergravity actions, I kept pointing out that the Ramond fields came with different powers of G squared. Do you remember this? All the NS fields came with 1 by G squared, the Ramond fields came without. And I didn't explain it then. Nobody asked me. And that was intentional. We will understand these powers of G string carefully now in our next round when we go back to the world sheet. There are 3 different natural normalizations of Ramond fields. Okay. I will explain this to you. This one loop versus tree level may feel odd, and from the point of view of a field theory, where every term in the bare action, if you had a theory which is 1 by G squared times something that's independent of G squared, one loop cannot cancel against tree level. Yeah. But that's not how string theory is, as I will explain to you. Okay, I will explain to you. It has to do with what is the strength of the field that transforms in a particular way under gauge transformations. So the explanation is different in the heterotic theory, where B was just an NS field, and in the type 1 theory, where B is a Ramond. Each has their own explanation, each works out, and I will explain both to you as we start looking at the vertex operators more carefully. Okay, let's postpone that. You can read what Pulchinski says, but you probably won't understand it till we look at the vertex operators better. Okay, so I propose that this ends our discussion of round 1 of our discussion on supergravity and anomalies. And now I propose we go back to the world sheet for a few lectures. We go back and look at the world sheet description of superstring. Our last discussion was extremely formal. We were looking at the mechanics of it on the world sheet, but we didn't know physics. Now we have lots of physics to explain, right? We want to see that we get the right massless spectrum properly. We want to see that we get all these anomaly cancelling terms. We want to see that these powers. So we have a physics goal. So let's go back to the world sheet with that physics goal. So maybe next lecture I can give you a recap of the world sheet for superstrings. Okay, and then the heterotic string, and then we will go back and examine some of these things from the point of view of world sheet. We will also go back and do things like try to understand orbifolds in the superstring theory, try to understand D-branes in the superstring theory. Okay, and then we will come back to gravity. We'll look at compactifications, ADS, CFT, that kind of